Hey everybody, and welcome to McArdle Math Academy. In this video we're going to be talking about finding volumes using calculus techniques or integration techniques. This example we're going to do is to find the volume of this figure that I drew here. The front of the figure, or the cross section of the figure, is a half circle, so it kind of looks like a greenhouse almost. So in order to find the volume, the first step is to draw a slice of this figure. So I'm going to draw the slice as follows, where my slice will be this little rectangle on the inside of my figure. Alright, so that it'll have kind of an area like this, and it'll have a particular thickness drawn here in blue. Alright, and this thickness, because it's in the vertical direction, I'm going to call this thickness dy. Okay, so the next step would be to kind of give some dimensions to my slice. So I know that this side is always 2 meters. That's constant, it doesn't change. But this side, and I'll draw this in red, this is not always 4 meters, because as we move up and down this half circle it'll change. So this is what we're going to call W. Okay? So once we have these dimensions on here, we can just start the integral problem. So that means we have to first find the volume of our slice. So now volume, we know, is always going to be the area of the top of the slice times the thickness of the slice. So the thickness here is dy. And the area, if we look at the blue area, is going to be the width, which is 2, times the length, which is 2, times the width, which we call w. Alright, but now our job is to make sure that w matches the variable that we see here as our integration variable. Alright, and so in order to do that, we have to come back to the main diagram here, and we have to think geometrically about this figure. And so to look at this geometrically, it actually helps to just draw the front, just draw the cross section. And we see that we have the radius here of 4, and we have w over 2 representing just this little half red segment. Now if we connect these with a blue line, we see that this is a radius of a half circle, so this also has a length of 4. Okay? Now back on the original diagram, let's do this in green. I know that the height of my slice is what we're going to call our variable y. Alright, so y starts down here and it ends way up here, and when we're at the intermediate point it'll be y. So therefore down on my geometric figure here, this will be y. Okay, so what we've done is we've created a little right triangle here, and we can use the Pythagorean theorem. So 4 squared is 16 is equal to y squared plus w over 2 squared, which is w squared over 4. Alright, and we can solve this for w. So we find that w squared is 16 minus y squared, all times 4, and we just take a square root. And that little 4 in the square root can come out, so we have w is 2 times the square root of 16 minus y squared. Alright, and this is what we get just from basic geometry. So now we have what we wanted. We have w expressed in terms of y, and we're going to bring that up to the volume of our slice. So when we plug that into the formula, we'll have 2 times 2 square root of 16 minus y squared dy. And that's the volume of our one slice from our original figure. And then all that remains is to set up the integral. So we know the integral, so the volume v is going to be the integral of the volume of our slice, which we just found. And all we have to do is look at what the variable of integration, which in this case is y, what that ranges from in our problem. So y ranges from 0 up to 4, and those become the bounds of our integration. So we have 0 to 4, and all we do is we plug this in. So I have 0 to 4 of 4 square root of 16 minus y squared dy. All right, that's the integral that would help us find this volume. We know that this will involve a sign substitution, but I'm not going to do that here in this video. This was more just for the setup. Hopefully this helps, guys, and I'll see you next time.